Sophia is a student from U Toronto. Let's see what she'll tell us about.
Well, thanks for the introduction, and thanks everyone for coming. Also, can everybody hear me all right? Okay, excellent, cool. So I'll be talking about a new technique we recently developed, which we call amplified amplitude estimation. And what it allows us to do is to refine estimates of expectation values. Okay, so let's get started. So I guess yesterday we had a lot of talks about simulating quantum systems, where we say, okay, we're looking at Hamiltonian simulation and we'd like to implement the time evolution efficiently on a quantum computer, which is great. We can do that very efficiently. The scaling goes like, poly log 1 over epsilon, log 1 over epsilon in the best case. But then what do we do with that quantum state, right? We evolve our time, we time evolve our quantum state, but then, yeah, what now? We somehow need to extract some information, right? And that's where usually we'll start thinking about expectation value estimation. So specifically, can you see my mouse? Yeah, perfect. Specifically, this setup we're considering is the following. We're assuming we have some quantum state psi and some operator A, usually a Hermitian operator, some observable we might be interested in. And we want to compute the expectation value of that observable within some error epsilon. Right? And so A might be, like in chemistry applications, we'll often think about A as being the Hamiltonian and the interested in estimating, say, the ground state energy of the system. It could also be the position operator if you're interested in, say, the mean position of some particles, etc. And often it's useful to consider access to our operator via some block encoding, which was also introduced yesterday, where the idea is you have some, like A will not be unitary in general, so we can't apply it directly in a quantum circuit, so we embed it in a larger unitary matrix, this U, and the operator will always be normalized by this, by some constant alpha, just to ensure that U will actually be unitary. Okay, and so one way we can estimate expectation values is this Hadamard test, right? And it's a very simple circuit. We just have a single ancilla qubit. We apply some Hadamard gates. We have a controlled application of our unitary. And you do a Hadamard again, and then you measure the top qubit. And then the probability of estimating this top qubit as 0 is given by this, right? It's just 1/2 and then 1 plus the real part of the expectation value. And if A is Hermitian, then we can also just drop the real part, right? Because the expectation value will be real anyways. And then once you have this, you can just simply subtract 1/2 from your estimate from the probability, and you get your estimate of the expectation value. Now, I guess there are two ways of actually extracting the expectation value. So the classical strategy would be to, say, run the Hadamard test n times. You measure, and then you just compute the sample mean. In order to do that within error epsilon, you will require order 1 over epsilon squared many samples. So you will have to run the circuit 1 over epsilon squared many times. And this scaling is also called the shot noise limited scaling. On the other hand, we also have coherent strategies, right, which is quantum amplitude estimation. And I'll briefly recap that later on, how that works. But the main point is that it allows us to estimate the expectation value using only 1 over epsilon many applications of the circuit encoding our expectation value. So it's a quadratic speed up over the shot noise limited scaling. Now, let's consider the case where the expectation value, the probability we would like to estimate, is very, very small. Specifically, let's assume we have a quantum state of the following form. So psi is a superposition over 0 and 1, and the amplitude of the 0 state is very, very small. It's some epsilon, or sorry, square root epsilon, and epsilon is a very small number. And what we'd like to estimate is this amplitude, right? So one way of considering this is to say we have a projection operator pi onto the state of interest, in this case the 0 state, and then we would like to estimate the expectation value of this projection operator with respect to our psi state. And now if we think again about our classical approach, if you're a bit more careful, then you realize that the number of samples we need is not strictly 1 over epsilon squared. You have this sort of additional tuning knob, which is the variance, right? So this is sigma squared. And if you compute the variance for this specific example, you'll find that it actually goes like epsilon times 1 minus epsilon. So the overall scaling is actually 1 over epsilon. So, and you can think of this as having some prior knowledge, right? We know that the amplitude is very small, and then we know that how the variance scales in this case. So that shows us that in this specific example, you can actually improve upon the shot noise limited scaling using this classical sampling approach. The question now is, of course, I also showed you this coherent approach using quantum amplitude estimation. And then, well, the question is, can we improve that scaling, or can we get a quadratic advantage of that scaling as well, which would be like order 1 over square root epsilon? And the answer is sort of yes. And this is where our technique comes into play. And I should say, so the way to read this is you're estimating an amplified amplitude. It's not that you're amplifying the amplitude estimation procedure. It's you first amplifying the amplitude, and then you're estimating this one. And so the idea is really that you combine the existing techniques, amplitude amplification and amplitude estimation, where amplitude estimation itself already uses amplitude amplification under the hood. And so what we're doing is we're using amplitude amplification to boost this very small probability to a larger probability, and then we estimate this larger probability or this larger amplitude using amplitude estimation. And one sort of intuitive way of thinking about it is, if you're familiar with the quantum amplitude estimation protocol, then it all boils down to estimating phases, where the phases, or where the probability you wish to estimate, which in this case would be x, is encoded as e to the I arcsine of x. And then if you look at the arcsine function, you can see it like close to 0. It's sort of linear, but as soon as you get close to 1, it sort of shoots up. So it becomes much, much more sensitive in a sense, right? So if you think about, like, if you make a small change, like if you have a small change on the sort of x-axis, right, you'll see a huge deviation in the arcsine of x. And that somehow allows you, in some sense, to estimate these probabilities close to 1 more cheaply. OK. And so the specific setting is as follows. So we assume we have access to, again, thinking about projection operators for convenience. And projection operators are not unitary, so again, we can't really implement them directly. So instead, what we're doing is we're encoding our projection operator inside a reflection operator, which is a unitary, right? So we have that pi is just the identity minus some reflection operator, about the state encoded in the predictor pi. And also, we assume we have access to a state preparation oracle, psi, which just gives us the state psi that we're interested in. And then the goal is, again, to estimate this expectation value of the projector, which we now write as follows. So we say the expectation value is some p naught plus delta, where the p naught is a known upper bound that we have. And so this means delta is a negative quantity, a small negative quantity. And the form of the upper bound is not super important right now. It's just chosen in such a way that amplitude amplification spits out the correct result exactly. And the idea is, so this p naught is some prior knowledge we have of the expectation value we wish to estimate. And this, sort of similar to the variance in the classical case, sort of gives us an additional tuning knob in our complexity scaling. Specifically, we show that in order to estimate this expectation value, we require order p naught to the 3/2 over epsilon times the delta, absolute value of delta, queries to our reflection operator and to our state preparation oracle. And then you can see in particular in this very specific regime, admittedly, where the delta, sort of the deviation, as well as our upper bound, are all on the order of our error, epsilon. Then the number of queries actually scales like 1 over square root epsilon. And of course, I should say, like, clearly, like, the delta should be smaller than the p naught, but this is the constant factor that's sort of hidden in the big theta notation. It's just this, right, we're talking about asymptotic scaling. Okay. So let me now move on to some more, slightly more technical details about how this whole thing actually works. So just to start off again, as a quick reminder, one ingredient is quantum amplitude amplification. So again, we have some, so the idea here is if we have some quantum state psi, which we project onto some good subspace with some probability square root p or amplitude square root p, and then the projection onto the bad subspace, the one we're not interested in, it was with amplitude square root 1 minus p. And what we would like to do is we would like to boost the amplitude of the good state close to 1. And then the way we go about this is by implementing a walk operator composed of 2 reflection operators. A reflection about the good state and a reflection about the initial state. And then you can see, if you work out the math, if you apply this walk operator repeatedly, mu times, to your initial state, then the probability of the amplitudes will now be of the form as written here, where the theta, where sort of your amplitude is now encoded as an angle, right? And so this is sort of the standard picture. If you write, or if you imagine psi lying in this unit circle spanned by the good and the bad state, then you have this angle theta here, and you just keep reflecting about sort of the good state, and then back to the, and then you reflect about the initial state, which brings you closer to the good state. And then now for quantum amplitude estimation, where the goal is now to estimate the amplitude of, say, the 0 state, is we're using amplitude amplification to get our amplitude in a phase, and then use phase estimation to estimate that phase. So again, here I have my walk operator, and then you can show that the eigenvalue is supported by psi of the form e to the plus minus I theta. Again, theta is this angle encoding our amplitude. And when you apply this walk operator repeatedly, you will never actually leave this 2D subspace spanned by psi and the state that you get when you apply the walk operator to psi. And then once you have that walk operator, what you do is you apply, or you implement phase estimation with that walk operator to extract the phase theta, which then allows you to compute p. Right, and just here as a reminder, this is the circuit for phase estimation, right? And the controlled unitaries that always appear in phase estimation in our case are now this walk operator, W. Okay, this is just a brief recap to know what we're talking about, the setup. So we're talking about for explaining amplified amplitude estimation, the goal is to estimate this quantity. Okay. So what we do now is we first boost our small amplitude close to 1 using mu applications of our walk operator. And this allows us then to construct so we have a new walk operator now, W prime, which looks very similar to the other one, except that instead of having just the projection onto psi here, we now have the projection onto the state we obtain from applying the walk operator to psi. And now we use phases, or we implement phase estimation with that new walk operator. And again, similar to the previous case, the eigenvalues of this new walk operator are slightly more complicated. The details are not super important. I just want to show you that this new amplitude depends clearly on our prior estimate or prior knowledge P naught and this delta. And the goal is really we know P naught, but we don't know delta. So the goal is to extract delta from this estimate. And so this is the circuit. It's essentially the same circuit as before. The only difference is instead of having a W down here, we now have this W prime operator down here as our controlled unitary. So the question now is, well, what happens if the amplitude isn't small? I told you that, okay, if we have this very small, epsilon small amplitude, we can use this technique to estimate it more efficiently. But if we think about the expectation value estimation example, then if we use the Hadamard test, the thing we return is actually 1/2 plus basically 1/2 what we're trying to estimate. So if we think that our expectation value is small, the probability that we get out from the Hadamard test is actually pretty large. It's very close to 1/2. And if the probability is close to 1/2, then we can't actually use this amplitude estimation technique. So that means we need a setup that directly encodes a small probability into the amplitude. And what we're doing here is using ideas from linear combinations of unitaries, obviously. And so just to remind you of the setup, so we have U, which is some block encoding of our operator A. And for simplicity, just assume now that A is Hermitian, because I guess that's sort of usually the case. And then the success probability of actually, the block encoding is sort of a probabilistic implementation of our operator A. And the success probability of actually applying the correct operator to psi is given by this formula here. And you can see it's sort of almost what we want, right? So the success probability is basically the expectation value of A dagger A, or A squared in the Hermitian case, which is fairly close to what we want. And then the natural idea is to say, okay, well, maybe there's a way that we can implement, or that we have access, I guess it's mostly assumption, that we have access to the square root of our operator. I think that was also mentioned in the talk yesterday. And so if we assume that we have access, or that there's a way to implement a fast square root of our operator, then we just do the Hadamard test with the square root of our operator, right? And then the probability will be exactly square root A squared, which is just A. Okay. So this is sort of the main ideas. Let me now briefly talk about some applications of these ideas. So the first idea is to use this technique to improve classical estimates. Say for chemistry applications, we may want to obtain some low-cost estimate of our expectation value using, say, density functional theory, which will not be very accurate, but it will be pretty cheap. And then, in this case, DFT would give us this P0, our upper bound, on our expectation value that we try to estimate. And then the idea would be to use this AAE procedure to refine the estimate that we get from DFT. Right, so we would use AAE to estimate the delta within some error epsilon. And again, in this very specific scenario where delta and P0 happen to be on the order of epsilon, then the number of queries to estimate this delta is on the order of 1 over square root epsilon rather than 1 over epsilon. And so the second application is to use A to estimate energies through gradient integration. So let's suppose we have some energy E, again, as a function of some parameter f. This might be like a path in the configuration space of your molecules. And then, just using the fundamental theorem of calculus, we know that the difference between the energy evaluated at s is equal to 1, say, minus E evaluated at 0 is just the integral of the derivative of the energy. And now to implement this numerically, we will have to discretize the integral, and you can do that using, say, Newton-Cotes formulas. And the idea is now that we're assuming we have exact knowledge of the energy at 0, and we like to extrapolate. We would like to use that as prior knowledge to estimate the energy at s equal to 1. And then there's this handy theorem, the Hellman-Feynman theorem, which says that the derivative of the energy is just the expectation value of the derivative operator. So h would be our Hamiltonian, and you just need to estimate the expectation value of this derivative operator. And so the advantage we could gain here is in certain cases, say, especially if the energy doesn't change much, this derivative operator might have a very small norm, very small one norm for encoding it. And in particular, like if the block encoding constant of this derivative operator is sufficiently small compared to, say, the block encoding constant of the full Hamiltonian, then doing a couple of estimates of the derivative operator might be cheaper than actually estimating the whole energy using the energy explicitly using the Hamiltonian. Oh, okay. This brings me to my conclusion. So the main takeaway here is really that we should look more into exploiting prior knowledge, because often we do have prior knowledge. And we showed that exploiting prior knowledge in a specific setting allows us to be the Heisenberg limited scaling in expectation value estimation. And this is, again, the scaling that we get. And in a specific regime, we can get this 1/√epsilon scaling. The question then is, of course, it would be really nice to figure out in which specific examples this technique may provide an advantage for practical applications in, say, chemistry. And if anybody's interested in further details, the paper is on the archive, and I'm happy to take questions. Thank you.
We're a bit over time, but one very, very quick question, if any.
So I didn't fully understand if the operator A, does it have to be positive semi-definite, or it can also have negative eigenvalues?
I guess for the square root trick, you probably want it to be positive semi-definite. Yes. Yes.
Thank you.
Well, I guess, or another option would be you could try to, you principally could split into a convex sum of positive semi-definite operators, estimate those separately, and then combine the result post the quantum circuit, basically. Yep.
Thanks.
Thanks, speaker.